typically what you would see that if let's say the switching frequency is constant, say 1 kilohertz, and you start running your motor all the way from 0 to 50 hertz. So effectively what you will see, the ripple part on the current keeps on increasing. Now initially it will be very small ripple, then slowly it will increase. The reason being that as you are going from here to here, you are changing your pulse number, and so the approximations are more crude, more inaccurate. That is why the relation with pulse number is very important. If you say that this is sufficiently high, see this may not be very visible when you take switching frequency of 5000 hertz for 0 to 50 hertz motor, because still even at 50 hertz the pulse number is something like 100. There would be difference, but it may not be very visible. You try doing the same with switching frequency of 500 hertz, you will see much more different behavior.
Same thing, sir. Actually, for some requirement, similar kind of thing was there from 50 to 400 hertz. So that is why this question came.
Yes.
Because the original frequency, switching frequency was 6 kilohertz. Then like fundamental that time initially was 50 hertz. Later on, the fundamental was changed from 50 hertz to 400 hertz. Switching frequency, because of converter limitation, we could not increase.
Yes.
So that is why
now you can correlate the pulse number, right?
Yes, sir. So then what we should do is, instead of using the formula direct as it is, in that we should try to put FSW. Instead of FSW, we should try to correlate with pulse number.
Yes. See how the pulse number has come down, right? So what you are saying is directly relatable here. So this we all need to keep in mind when we are dealing with systems, any frequency. Let us say when I give example of 50 hertz motor, then same phenomena you will start observing even with 1 kilohertz or 500 hertz switching frequency. When you are dealing with such systems where fundamental frequency itself is going like 500 hertz or so, you will start seeing that even at 5 kilohertz or 6 kilohertz, because that difference is coming down. The ratio is coming down. Understand my point? So each and every pulse which you are injecting for realization of the voltage, yes, you are realizing some voltage level here, but is this matching with what you are trying to realize? You might be realizing something like this, because the duration is little bit significant compared to your whole fundamental cycle. If this is 360 degree, this may be like 18 degree or 20 degree, something like that. Now this variation will be significant in the actual voltage, whereas we are realizing this. This creates further voltage error. So despite having same intervals, let's say T1, T2, T3, T4, this factor has increased. So what we are seeing as voltage error, which is like VDC by 3 minus VDC by 3, and this, it may look like this. Understanding my point? Because our actual voltage is changing. It's not fixed constantly. So the difference will also be like a changing waveform, not a fixed waveform. So which is what creates the difference. Good. So this analysis, again I am saying that it is okay, more or less it will match, but you should be able to correlate with, is your voltage error only this what you are seeing on that, or is it something more because of lower pulse number? Correct? So all of you keep this in mind when you are dealing with any system. What is important is what is the ratio between the two. You may have 10 kilohertz switching frequency, as I told in the beginning, one of the classes, but your fundamental frequency itself may be 2 kilohertz. So you can't do anything. It will have poor performance despite having so high switching frequency. So the factor which is responsible for good performance is the ratio pulse number. Good. So we have discussed the analysis and all that, and now see yesterday's question what Sampan asked. So there was long discussion on that. But see, when we are doing that, the implications we are not observing what it is actually doing to our system. Understand, Sampan, what I'm trying to say? See, if we are simply, let's say, blindly, we are having carrier peak between plus minus 1, we have changed to 0.8. Now, whatever values we had, let's say, remove all this, whatever values we had, say, MR, MY, MB, as per this plus minus 1 is, say, 0.2, 0.4 and minus 0.6, right? Now, this is effectively scaled up by the ratio 1 by 0.8. So 1.25 times effectively. So this becomes a 0.25, and then this becomes something like 0.6, then this becomes something like 0.75. Understanding my point? So I don't know, 0.75 or 0.85, how much it would be? This is perhaps 0.5 only, right? Yes. Fine, right? This is correct. So effectively, we are now dealing with new numbers. And still, that what you are claiming that your ripple has gone up may not be true actually. You need to recheck the analysis. Okay, but effectively by changing this, we are now dealing with a new modulating signal values. So that is why this is something like our reference. We must not disturb this unless it is some very special requirement, which at least in this course we will not discuss. But if somewhere you are designing some very special PWM where you need to change the carrier peak or something, that's a very different requirement. There everything will be different. The analysis would be different. So we will see what happens when we try to cross this boundary. No, this kind of thing we will discuss today. So for example, I have taken this waveform here. Now let us say one of the limitations of sine triangle PWM, it's very easy and nice. No, we have 3 modulating signals getting compared against the carrier, and we are finding our PWM voltages. Everything is nice. Now the problem is that the peak of the modulating signal can only reach up to this boundary. Understand my point? So m sine omega t, which is the MR value, this will vary between plus minus m, right? The value will vary between plus m and minus 1 sinusoidally. Now this m can be or is actually restricted to this. 0 also can be included. This is restricted to this. What happens if you try to go above that? What will happen? So something when we are within this duration, so here carrier frequency is little lower, but for illustration I am using this. What is happening that when it is within this range, within the height of the carrier peak, what you have that basically regularly you are having intersection of the carrier and modulating signal. You have regular intersections coming everywhere. So which means effectively you are generating pulse. You are having PWM pulse like this, or it may be like this, but you have pulse everywhere. Correct? Comparison is happening everywhere. But let us say for some reason you try to cross this boundary m greater than 1. Say m becomes 1.2. What will happen? The same modulating signal may look like this. Now you see the difference. For this entire duration, in fact, the last intersection happened here. So for this entire duration, you don't have any intersection between the carrier and modulating signal. What is the impact of that? You will have plus VDC by 2 continuously there for this entire duration. And similarly minus VDC by 2 for this entire duration effectively. So your PWM may actually, which was looking something like, if I draw here, when you have this plus VDC by 2 and minus VDC by 2, there are switchings everywhere. No, whole waveform will have switchings like this, correct? And it will keep going. Now when you try to have modulating signal, say let us say more than 1, say m equal to 1.2 or so, what will happen? You will have a duration where you don't have any switching, you don't have any comparison. There will be a blank plus VDC by 2. And similarly on the negative half cycle, you will have minus VDC by 2. And rest of the waveform will be switching as it is. This is how your PWM may look like. There will be a blank time where there is no PWM, it's constant plus VDC by 2 voltage given. Or on the negative half cycle, you may have minus VDC by 2, which is given. Now what this will do? What will be the impact of this? When you are having intersection everywhere and pulses everywhere, you are sure that you are trying to realize the VRO average as MVDC by 2. Because everywhere you are trying to realize some voltage level. And so this relationship is intact. So this range of modulation index, when you are having between 0 and 1, this is called linear modulation. Because you have the understanding what you are switching over here and what you are realizing in the system. Correct, right? Because we are doing on basis of every sub-cycle and it is matching. Yes, correct. So we know that if we feed this value of modulation index, so let's say MR I can write. So if I know that, let's say my modulation index is 0.6. So I am feeding effectively MR equal to 0.6 sine omega t. So I know that what VRO I am going to get on average, or what VRN I am going to get on average. It will be simply 0.6 into VDC by 2 times of sine omega t. You understand my point? This linearity is maintained until you are within this boundary. Even equal is also okay. You are just touching the boundary. Now, this relation gets violated when you come to this factor, this kind of thing. Here you do not have any comparison. So you can't say what is your value of average VRO in this duration. Certainly it will be high because it is continuously on. So this VRO now is not related to MR in this fashion. It may be different, it may be more. Understanding my point? So this place where we are crossing the modulation index, or just greater than also is fine. Wherever you start losing the pulses, this is called over-modulation zone. So effectively what has happened that our linearity is gone. So sometimes you may call it non-linear zone also. You are giving some MR value, say 1.2, but you cannot say that my VRO would be 1.2 VDC by 2 times of sine omega t. This you cannot say. May happen, may not happen. Actually, it will be higher than this. Understand my point? This is what is called over-modulation zone. So, sine triangle PWM, what restriction we are having is that our range of modulation index is only limited to this 0 to 1. And effectively, the maximum peak phase voltage, what we can realize is VDC by 2, which means we are having 50% of DC bus utilization. So the idea is to increase this utilization, which means going beyond this number. So what can be done? So somehow if you see the problem is when this peak has touched the boundary, the modulating signal peak has touched the boundary. That is the whole problem, nothing else, right? So what we have basically, this peak is going and it is touching here. So if you can somehow avoid this peak from touching this boundary without changing anything else in the system, then you can achieve more than this. You can go for some higher modulation index, more than 1. So which means you can get higher DC bus utilization than VDC by 2. How it may happen? So generally the suggested way is try to add something as common mode. Common mode, you know, right, which is common for all 3 phases. So let's say what could be common for all 3 phases? Let's say a third harmonic voltage.
Sir, sorry to interrupt you, sir. Sir, sometimes I face a problem that slide does not change and you move to next slide. So
Is it lagging for all of you?
No, sir.
No, sir.
Okay, then I think some internet issue on your side.
yes, sir.
Now is it visible? Is it visible, Sampan?
Yes, sir. Screen is visible, but I think it is previous slide.
Which previous slide? What you are seeing now?
Sir, I am seeing the first figure that you draw linear modulation and touching the peak.
Which is what I am teaching now.
Yes, sir.
Do you see my pen moving here?
Yes, sir. Yes, sir.
Then fine, you are there.
Yes.
Okay, so now the idea is to inject some common mode such that we can reduce the peak value without changing anything else, right? We are not changing anything else in the system. So inject some third harmonic. So third harmonic is basically common mode for all 3 phases, because all this omega t minus 120 that comes back to the same thing effectively. So what we can do, let's say if we add some small amount of, not very large value, so a small amount of third harmonic to this system, say something like this. Third harmonic means it will have 3 cycles within the fundamental cycle. So something like this. Now what will be the effect of this? What will be the result of this when you add something like this? So the waveform, resultant waveform of this blue and black, when you add simply, you see that the peak for the black waveform is negative. So certainly it will subtract something from the peak of the blue waveform. And similarly here, when the blue waveform is negative peak, it is having positive peak. So it will subtract something here. So the resultant waveform may look like, is the green waveform visible?
Yes, sir.
Yes, sir.
Something like this. The peak is now dipped to a lower value.
Sir, it is not visible to me.
You just wait.
Yes. Yes, sir. Now it is visible.
Is there? Is it visible? So what has happened effectively that by injecting this common mode, which is third harmonic waveform, you have brought down the peak to this value. Now there is gap between the peak and the portion where it may touch the boundary. You see that gap? So which means now you have the flexibility to increase your modulation index beyond 1. You understand my point?
Yes, sir.
So effectively by using this kind of third harmonic wave, you can increase the DC bus utilization in this manner. So what may happen now? Now you can go even for higher fundamental waveform, something like this. And still you can have appropriate third harmonic which will keep the resultant waveform like this. Now these 2 points will touch the boundary. Understand my point? So everywhere you have intersection, everywhere you have the PWM continuity. So we are not losing any pulse. We are not missing out the linearity. You understand my point? Correct?
Yes, sir.
So if we go into the details of this, the whole derivation I am not presenting here, just telling few methods what are there in terms of carrier based PWM. So this is called third harmonic injected PWM. This is not sine triangle PWM because your modulating signal is no more sinusoidal. It is having a different shape. So this is third harmonic injected PWM. And so here we have the flexibility to take modulation index up to, I think, 1.15. And this happens when your M3 is something like capital M by 6. Okay, you cannot have any random number for the third harmonic, right? There has to be a factor of that. The factor is 1 by 6. So some k times of, let's say, k is the factor I am saying. So M3 could actually be k times of M sine 3 omega t. Because this is common RYB. Same waveform will be added to all RYB. So I can write my new modulation index MR star as MR, what is M sine omega t, plus this M3, which is Km sine 3 omega t. Similarly, My star, which is new modulating signal, My plus M3, Mb star, which is Mb plus M3. Now straight away you can see this is common mode, so which is not going to appear in the line to line voltage. For obvious reasons, it will get cancelled out. So line to neutral will not contain this third harmonic. You understand my point? Correct? But what it will change basically? By adding so, if it is not reflecting in the line to neutral voltage, what it is changing? You are still realizing, this, say you have the carrier and you have the modulating signals. And you are having the pole voltage waveforms, say R can come here, then Y, then B, all these things can be there. Effectively, what you have changed?
Change MR, MY, MB at the position spectrum.
That is okay. First change what you will observe is that you will have MR plus MY plus MB equal to 0. But MR star plus MY star plus MB star will not be 0. Of course, because there is common mode added. this will be actually 3 times of M3. So which means if this is your original MR, MY, MB, now you have changed everything by same factor. This also increased by something, this also increased by something, this also. You are just adding the same number to all three. So this relation may not hold now for the new modulating signals. Actually, it will be this. And so effectively, your intervals will change. So only difference you will see in T1, T2, T3, T4, but this will be arranged such that still you are realizing the same VRO, which is MR VDC by 2. But intervals are changed. So our analysis will see the same VDC by 3 and minus VDC by 3 kind of structure, but with changed duration. Something like 0 and then plus VDC by 3, minus VDC by 3 and 0. This change duration will actually help us in achieving more DC bus voltage. So DC bus voltage can reach up to this maximum value now, VDC by root 3. If you use a factor K of 1 by 6. You can have maximum this much peak phase voltage. Earlier it was VDC by 2, right? Now it is VDC by root 3. Remember the number, it was 0.5 VDC, now this is 0.577 VDC. So what will be the effect of this injecting third harmonic is that 400 volts motor what you were trying to run. Now here it was needing some 753 volts. How much it will be here? Can you compute quickly?
So 868.96.
You have gone higher.
434.
No, 434 is not the correct number. How are you computing? 400 divided by root 3 into root 2. Correct? This into root 3. That is all. Earlier it was 400 by root 3 into root 2 into 2. Now it is into root 3. So it should be lesser. This is new VDC. Peak phase voltage I am saying, right? So you have to equate the peak phase voltage with this. What is peak phase voltage? 400 by root 3 into root 2. That is the peak phase voltage. Equate it with this. Now what is the DC bus voltage?
566.
560?
566.
So this may be little lower. No, this how
Yes,
much?
sir.
This one?
This one is 653.
653. Correct. So see, almost 100 volts of reduction in the DC bus voltage for the same motor. So this is the advantage what you get if you have something like this getting injected into the system. And this is happening for this factor K equals 1 by 6. If you change this factor, you may not get this DC bus utilization. You may get something else. So for best DC bus utilization for third harmonic injected PWM, you should have this much amount of third harmonic injected into the system. 1/6 of the actual fundamental amplitude. Am I clear here?
Yes, sir.
Okay. Now what happens, let us say, because your durations T1, T2, T3, T4, these are changing, this may actually also affect your current ripple. So what you will observe that instead of going very high on one side and then coming down slowly to lower value to 0, it may actually get distributed something like this. So this has the capability, this divided and new time interval has the capability to bring down the current ripple also. So it has the capability to reduce the peak to peak ripple in the current because intervals are different. You may not be going so high on one side. Understanding my point? So to get the best possible current ripple from the third harmonic injected PWM, the factor what is suggested is 1/4. Now see, these numbers are different. One is giving you the best DC bus utilization. The other number is giving you best current ripple. So you are appropriately changing the intervals. On one side you are trying to get this, other side you are trying to get this. Best peak to peak ripple. So we can use third harmonic in multiple ways based on our objective, what we are trying to do. So two prime objectives are there here. One is if we can increase the DC bus utilization, and second objective is whether we can reduce the peak to peak ripple to its best value, best possible value. And the factors for these are different. You understood the factor, right? I am writing M3 as K times of capital M sine 3 omega t. This factor K I am talking about. Fine? So
Yes,
this
sir.
is one.
Sir, but when K is equal to 1/4 and like if we take M value higher, like then also we'll cross the over mod, like we'll reach into
cross. It will cross, but it will not be able to reach up to this. It will be somewhat lower. See, DC bus utilization is 0.5 for sine triangle and best is 0.577 when you have K equal to 1/6. Other number may be somewhere in between. Understand my point?
Yes.
This is what I am saying. The other number may remain up to some 0.5, say 5 or 0.57, may not reach up to this. But what the other number will ensure that you will have best peak to peak ripple or least peak to peak ripple. That much assurance this will have. Am I fine? Clear here?
Yes, sir.
Yes.
Good. So this is the class of PWM, carrier based PWM, which is called as third harmonic injected PWM. So we may use this also very often in our motors and other applications to reduce either the peak to peak ripple or increase the DC bus utilization. All these things we can do. Now, few more PWM techniques are there which are again carrier based. So I will try to have a quick run through that and then we will close this chapter. So maybe one more I will talk about, which is basically called as the bus clamping PWM. Now bus clamping PWM is more related to reducing the switching losses, reducing the switching frequency effectively. To improve the switching losses, we have to reduce the switching frequency. So what is suggested that in bus clamping PWM, that again you add a common mode such that now all the things are happening with respect to a different common mode. Now you add a common mode such that we do not have any comparison, let us say in this 60-degree interval, say from here to here, which means what? This gets clamped to this peak value. And similarly here as well, you clamp this modulating signal from here to this negative -1 value, which means we are not switching in this interval. Of course, there are chances that we may lose linearity if your switching this carrier frequency is very small, but this is something for high switching frequency cases or high pulse number cases. We can afford to have this discontinuity in between in the PWM, or this blanking time we can afford to have. Still, it will maintain more or less the same linearity, and there is common mode injected, which will of course subtract out in the line-to-line voltage. So effectively what we try to do, we add a common mode, which is the difference of these two levels, which means the common mode for R will be 1 minus MR for the duration, say 60 degree to 120 degree theta. And similarly on the negative side, it will be -1 minus MR for 270. So here it goes from 240 to 300 degree. This will be the common mode, which is resulting after the R phase. You understand my point? So due to R phase clamping, this common mode is coming up, or from the R phase clamping, this common mode is coming up. Now this is only valid for this interval, 60 degree on the positive side, 60 degree on the negative side. How about other intervals, the gaps over here? So these common modes will be based on, say, Y or B phase, here also Y or B phase. Because every modulating signal which is going close to its peak, we are trying to have this kind of clamping. We cannot have unbalance, right? So we have to have the same common mode injected everywhere, plus the waveform should also look similar. So what we do that, we clamp R phase here, Y phase here, positive peak I'm talking about, B phase here. Correct. Then similarly on the negative side, we will have clamping for Y phase here, then B phase here, R phase here. So these 6 common modes, every one occurring at 60 degree interval, we are going to add in all the 3-phase modulating signals. So if I write the whole, complete common mode, it will be something like here we have the Y phase coming over there. So -1 minus My. This will be for 0 theta 60. Then we will have R phase here. So 1 minus MR for 60 theta 120. Then we have B phase negative -1 minus MB 120 theta 180. Then we have Y phase peak 1 minus My. So 180 240 here. Then we have R phase negative peak -1 minus MR. And then we have B phase positive peak. So 1 minus MB 300 to 360. You understand my point? These are segments of waveforms which are getting added together to make the complete common mode. Now how this common mode will look like actually? It will look like, I can draw here. So for this portion, it will be something like this. Then for this portion, it will look something like this. Then for this portion, it will look something like this. And again for this portion, it will look like this. Again for this portion, it will go like this. And for this portion, it will go like this. Do you see the waveform here? This is the resultant of what I have written mathematically. Now, if you see closely, no, this is, you can say, one cycle of your common mode, and which is repeating 3 times within the fundamental cycle. So this is again some kind of third harmonic or triplet harmonic, you can say. This is not third, but something which is repeating itself at 3 times of the fundamental frequency. So some triplet harmonic is coming over there. Again, that will come as common mode and it will cancel out. But what that will result into, that your R phase, okay, if I draw on this R only, it will now look like this. You see the difference in the waveform R phase. It is coming down below than the zero crossing. And similarly, it will start from little bit higher. You see the difference? The sinusoidal signal has become, okay, perhaps I can draw with green for clarity. Do you see the change in modulating signal, how it is looking now? So this is what we have added. No, we have got by adding the modulating signal, which is sinusoidal, and this third harmonic or triplet harmonic kind of common mode. And this common mode here, we are not having any factor. This is not any factor. This is directly what our modulating signals are. On basis of that, we have generated. So this is a new class of PWM, which is basically called bus clamping PWM. There are many ways to do bus clamping. The meaning of bus clamping is that you are clamping your modulating signal to the positive or negative peak. In effect, what will happen? Your PWM will get clamped to the positive VDC or minus VDC. And we are ensuring that this is happening at sufficient switching frequency or sufficient carrier frequency, so linearity is not lost. This is not something for pulse number 9 or 15. We may lose a lot of things over there. Correct? This is something like when you have pulse number of say 33 or something like 50, how much it will be? 51, then it could be some 57, something like that, higher pulse numbers, right? You understanding my point? So this is called, when we classify the type of PWMs, this is broadly called bus clamping. What we are clamping? We are clamping the VRO or VYO or VBO to either plus VDC by 2 or minus VDC by 2. This is the meaning of bus clamping. It is clamped to either plus positive DC bus or negative DC bus. Now when we are doing this continuous clamp kind of thing, so first classification is that you can say whether it is 60-degree continual clamp, or you can have a method to split the clamping in 2 parts, say 30-degree on this side, 30-degree on this side. That will be called 30-degree split clamp. Another way to say this continual clamp, yeah, what I have written, the continuous clamping, and this will be discontinuous clamping. Now you can also do, you can have 40-degree here and 20-degree here. That is also fine. Understanding my point? So effectively, when we do clamping for this 60-degree positive, 60-degree negative intervals, our switching frequency is coming down to 2/3 of the actual switching frequency. And so the switching losses are also almost 2/3. So this way we save something on the switching loss side. Now, for which system it is advisable to do continuous clamp and for which system it is advisable to do split clamp, you can simply understand by let's say if I draw the current waveform which is almost in phase with the voltage. So obviously the current is higher in this zone, the 60-degree middle of the the waveform. So which means if you do clamping here, we can effectively reduce lot of losses because current is high over here. Understanding my point, Ashish?
Yes, sir.
So whenever current is high during the middle of the the half cycle, then the 60-degree clamp or continuous clamp is preferred because higher current results into higher switching losses. So if we are clamping during this, we are effectively ignoring or avoiding lot of switching losses. Now, if you have, let's say, a lower power factor, say your current is here, having some lower power factor angle, almost 90-degree out of phase or something. So what will happen? Near this zone, which is, we have split the clamping. Near that, your current is slightly higher. You see that? And during the peak, it is very low value, almost to 0 for 90-degree lag. So not much advantage of having bus clamping at 60-degree. What we can do, we can have 30-degree clamp and we can reduce the switching losses effectively in case of lagging or leading power factor, which is like high power factor angle if we have. Correct? So for inductive loads or any other load which is having very low power factor, that we can use this kind of split clamp to avoid lot of switching losses. And the modulating signal will of course not look like this, what I have drawn here. It will again look like some auto rickshaw having two headlights. So one may be here clamping and another may be here. So it may look like this, little bit funny. And if you have uneven, say 40-degree clamp here, 20-degree clamp here, then it will be like something like one headlight is broken. So these are different techniques which we have for the carrier-based PWMs, bus clamping or third harmonic injected or normal sine triangle. So these all we can do to make our system better. We can use all these things to make our system better in terms of either switching energy losses or DC bus utilization or reducing the current ripple and so on. So up to this will be like part of your MTE, and after this, once the MTE gets over, we will start the thorough analysis of space vector PWM. Is that fine?
Yes, sir.
Good. So,
sir,
yes.
Sir, in case of two-level inverter, here we are losing that relationship, that switching frequency equal to carrier frequency, I think.
Yes. That's why I said this method is not applicable for pulse numbers like 15 or 9, because you will have effectively large blanking. But when you have sufficiently high pulse number, the other switchings are balancing somehow this. You see the change in shape of this modulating signal, right? This is kind of balancing that blanking time. So linearity is maintained. You are not simply crossing the range of carrier or the boundary of carrier, but you are having a common mode which will somehow balance that.
Sir, I didn't understand by how we can say linearity is still maintained.
You try and see.
Yes. Yes, sir.
Neelam, you were asking some question.
No, sir, by mistake that.
Okay. So if any more doubts are there, you can ask.